Here's a thunderstorm. Here it is in the developing stage. In a developing stage, a thunderstorm has just reached the level of free convection. The air of the cloud, the temperature of the cloud has become warmer than the air around it. And we have updrafts. The cloud is now growing and building. Pretty soon, it has squeezed so much moisture by rising and squeezing that cloud that it begins to start to rain. They're going to ask you on the test, how do you know if the storm has reached the mature stage? And the answer is, what do you think?
Precipitation.
It starts raining, you got it. Exactly. If it's raining, then it's in the mature stage. Now the dissipating stage, you can't tell that. There's no more updrafts, there's just simply downdrafts. Now, this is where they show up the best on radar. But I want to tell you, you'll get a heck of a rough ride right here. So anytime weather radar tries to tell you that they're showing, some precipitation up ahead, if it's any kind of precipitation, very likely if there's thunderstorms around the area, it's about ready to turn into the mature stage. And the mature stage has updrafts and downdrafts of thousands of feet per minute. Vertical shears of 5,000 to 6,000 feet per minute, enough to break any airplane in two. So keep that in mind. Also, as we have rain falling down, the rain is evaporating on the way down. And as it evaporates on the way down, it causes cooling. So while we have the warm air going up, we have a shaft of cold air from the evaporation coming down right next to it, increasing its speed as it goes down, making this strong shear. Well, if you talk about thunderstorms, you have to talk about hail, all right? Here's hail damage. Unbelievable. Look at that airplane's wing. That was damaged by hail. Now, I'd like to tell you a little bit about hail. Now, you can encounter hail in clear air. In fact, they ask that on the test. I want you to know you can encounter hail in clear air underneath the anvil. Here's an anvil top. You see, the way the thunderstorm works is it of course has these cycles. I mean, it has this up and down drafts in the mature stage. So a hailstone is simply started out as a little raindrop. It just made about 15 round trips to the top of the cloud and back down. Right? Now, how do I know that? You might say, well, how do you know it made 15 round trips? Well, I'll tell you how I know. I know. I'm going to tell you a fact. It's a fact that if you freeze water fast, it freezes rather cloudy. And if you freeze water slowly, it freezes clear. What would you think if you took a hailstone that was as big as a golf ball, you cut it open and you saw 15 alternating layers of clear and cloudy ice? You'd say that thing must have made 15 round trips because it freezes fast up here and slow down here. That's exactly what happens. If you cut a hailstone open, a big one, you'd see it had alternating layers of clear and cloudy ice. See, they make a bunch of round trips up here. But up here at high altitude, there might be 100-mile-an-hour winds. 100-mile-an-hour wind finally catches that hailstone and throws it out of the anvil. So the anvil top is a bad place to be, under the anvil, because you can encounter hail there. What else does that anvil tell us?
Direction the cloud's going.
Right, that tells us the direction that the cloud is moving. The reason for that is, the reason it of course spreads out this way is because the wind is so strong that the wind is sort of steering the cloud, and the cloud has less definition up here at high altitude, so it spreads out that cirrus anvil out there. Okay, so what do we know about hail? Hail has alternating layers of clear and cloudy ice, and we know that it is produced in the mature stage of a thunderstorm. That's what we know. And it also can be encountered in the clear air beneath an anvil. Oh, okay. I mentioned to you about squall lines, and I told you that the squall line is found ahead of cold front. So I just drew one in here ahead of a cold front. And it is defined as a solid line of cumulonimbus clouds. Oh, okay. I want to talk to you a bit about icing. I want to talk to you about structural airframe icing. Structural airframe icing. Now, I want to tell you that structural airframe icing, we only get this around freezing temperatures and below. Do not confuse this, class. Do not confuse this with carburetor ice. Carburetor ice, because of evaporation of the fuel and the drop in temperature there, you can get that at temperatures 50, 60, 70 degrees or so. But structural airframe ice, you can only get that at freezing temperatures or below. And you can only get it in precipitation. You must be in precipitation to get to get airframe ice. Now, the freezing level, what is a freezing level? If you hear someone say the freezing level is 6,000 feet, that means below 6,000 it's above freezing, at 6,000 feet it's freezing, and beyond that it's below freezing. Just because you hear them forecasting icing in the clouds above the freezing level don't think that just because you fly above the freezing level, if there's no clouds, that you're going to get ice. See, that's not the case. You got to be in precipitation and at the freezing level or above. So I hired one person, one of my students one day told me we couldn't go today. He told me the freezing level was 4,000 feet. We couldn't fly across country. It was clear as a bell out there. I said, well, it's clear. He said, I know, but they forecasted ice above the freezing level. You know, but you can't get ice in clear air, right? You only get ice in precipitation, clouds or rain. Now I want to tell you the most serious kind of ice is called clear ice. More specifically, though, it's freezing rain that produces clear ice. Now there's two main types of ice, clear ice and rime ice. And the type of ice that you get is dependent on the water droplet size and the freeze rate. Let me take a moment to explain that, please. Sometimes we have a day when we actually have a temperature inversion. The air, maybe the ground has been super cold. It's been sub-zero temperatures. And we have warm air coming in. The warm air up at maybe 6,000 feet, the temperature might be as warm as 50 degrees Fahrenheit. But because of the iceberg effect, or the refrigeration effect of the ground being so super cold, temperatures at 2,000 feet or 1,500 feet might be right at freezing. So we got rain that's formed up here at 5,000 or 6,000 feet in the warm air, and that raindrop falls down. This is a large water droplet. It strikes your wing and spreads out over your wing. What we have is a slow freezing of a large water droplet. This would be called clear ice or freezing rain. All right? Now, so it's a slow freezing rate, it's a large water droplet. Now, let me tell you that to contrast that with rime ice. I'll talk more about freezing rain in a minute. Rime ice would be if you were in had small water droplets, such as in a cloud, and the temperature was way below freezing, maybe below 15 degrees centigrade or more, below 0 centigrade. Small water droplets in stratus clouds, you could get possible rime ice. But generally that ice is so that it builds up and evaporates almost as fast as it's building up. It's not as serious as ice that you get right around the freezing temperature. That's the most serious, is right around freezing, at least for private pilot flying and so on. Anyway, so for the test then, they're going to ask you what kind of ice, how do you determine what kind of ice you're going to get? And the answer is, the ice that you'll get is dependent on the water droplet size and the freeze rate. In other words, large water droplets, slow freeze rate is clear ice. Small water droplets, fast freeze rate is rime ice. Now there's another kind of ice, and that's called mixed ice. Mixed ice is where you actually have maybe large water droplets, or let's say you have small water droplets and a slow freeze rate, for instance. See, in other words, you have the water droplets for rime ice, but the temperature for clear ice. That's where you get what's called mixed ice, sort of mixture of rime and clear ice. Now they're going to ask you on the test what type of clouds are associated with what kind of ice. And the answer is, well, what kind of clouds have the biggest water droplets? Cumulus. So they'll want you to say on the test that you have cumulus clouds for clear ice, you have stratus clouds for rime ice. Let's get back to talking about freezing rain, since freezing rain is so serious. Let me tell you how serious freezing rain is. Freezing rain is so serious that if you were to fly along in that situation I described a few minutes ago, and you began to get freezing rain on the airplane, I can tell you that in a 172 where you're cruising along at, say, for instance, 110 knots, I can tell you that within 1 minute, your airspeed could easily be back to 95, and you could put full power on to try to maintain forward speed, and your speed would continue to drop off. Within about 3 minutes, your airspeed could be down as low as 70 knots. You're getting close to a stall. And the aerodynamic shape of your wing is changing so that your stall speed is increasing. You might be flying right on the edge of a stall. Your stall warner won't work because it's all iced over, right? It's on the leading edge of the wing and it's been long iced over. Here's what you've got. You've got the perfect prescription for a fatal accident. Your thrust is decreasing because it's getting ice all over it. Your lift is decreasing because the shape of the wing is changing. The weight of the airplane is increasing because of the weight of the ice on it. And your drag is increasing because simply the ice all over the plane and the increased nose attitude required to keep the plane flying. Not only that, we got everything going against us. The stall speed is increasing. So we're getting closer to a stall. And not only that, but the higher the attitude of the plane is to maintain lift, the effects of the ice lean increase. In other words, however much ice you got in the first 2 minutes, you might get additional ice in the next 2 minutes. Well, I can tell you that within a period of 3 to 4 minutes after the situation I just described, full power and you're on the edge of a stall. The only way you're going to keep that thing flying is to put the nose down and dive it to the ground. You're going to be coming in like the shuttle returns, all right? You can be coming in at an angle like this, all right? Now, and they don't make a whole lot of runways that are all lined up with you and everything in a 6-mile long runway, all right? Now, I would like to tell you that if you got in such a situation, of course, the first thing to do would be to remember what his airworthiness told you. And that is that the end result could be in 3 minutes fatal. So what you better do, the first thing is start a 180-degree turn. As soon as you find yourself in icing conditions, you better start a 180-degree turn. Simultaneously, I am guaranteeing you that if you're in freezing rain, it is warmer above. Put on a power and start climbing at the same time. Now, I'm not suggesting you climb up in the clouds without an instrument rating, but assuming you can still maintain ground contact, climb to a higher altitude. You'll get into that warm air. I guarantee you, if you have freezing rain, you've got a temperature inversion and it's warmer up above. But start a 180-degree turn and get out of that. You have no business being there. Okay? That's what you want to do. Now, if you ever found yourself so coated with ice that you didn't do what I had said, and now you realize you're in a pickle, and you can't hold altitude, and you're going to have to make some kind of forced landing because you can't hold altitude anymore, I want to tell you this. Your stall speed is greatly increased. And I can tell you accident reports of pilots that have had to make forced landing that were killed in the last few minutes of their flight because while they were coming down, gliding in, of course their stall warner doesn't work, but the ground witnesses reported the last minute was the pilot was rocking wildly left to right and then he crashed. You see, what happened was his stall speed was so increased as he just started to flare out, all of a sudden the plane started stalling, he couldn't control it, and he lost control of the airplane and crashed. So if you have to make a forced landing, or if you have to land on even any runway, and you've got ice on that wing, plant it on the runway. Fly it onto that runway. Keep up some extra speed, because you're operating dangerously close to a stall. Also, you're a test pilot. They don't test this plane with this kind of ice on board. Nobody knows how the plane's going to handle. See? So be prepared. If you put down flaps, the whole characteristics of the plane may change. You just be alert for as you try things like putting down flap, putting out the landing gear, things like that, the whole plane's flight characteristics may change. But the one thing is, if you have more speed, you'll maintain better control of the airplane. Of course, it's more dangerous to land on a rough field, of course, with a lot of airspeed. Okay, I want to tell you that as you fly around mountains, I want to tell you that on the downwind side, the so-called leeward side, there are downdrafts. And these are very serious downdrafts. You want to remember that as you try to fly across the Rocky Mountains, where there's strong winds and downdrafts, that you might think you can clear that mountain. But the fact is that the downdrafts prevent you from clearing it. You might even on your altimeter show you're going to clear it. But as you get close to it, the downdrafts bring you into the mountain. So I want you to know this. As you fly towards a mountain range, approach that range. Let's assume this blackboard is a mountain range. This is the top of the mountain. Approach that range at an angle so that you can turn away. Also, keep in mind that a lot of times the range comes out like this. So here you are on top of these mountains. It's sometimes tough to turn around if you're coming straight onto something. That's why you want to approach it at an angle so you can turn around if you have to. Now, one time I went to a safety meeting where someone talked about mountain turbulence. He had been to a special mountain turbulence school, mountain flying school. He talked for an hour about mountains and mountain turbulence. And you know, the one thing that was absolutely, by far, the most important thing to know about flying in the mountains, he mentioned it probably 10, 12 times, but he didn't emphasize that this is the single most important factor about flying in the mountains. And that can be summarized in one word. And that word is wind. All right? Wind is what causes mountain turbulence. Now, if you want to know when is it safe to fly to Aspen, I'd say, well, when it's not windy. That's when it's safe, all right? And if you want to go to Aspen and the weather at Denver shows that you have a wind of 330 degrees at 20 knots, gusts to 30, and the weather at Grand Junction is windy there also, you better rent a car, all right? Don't try to fly in there with a naturally aspirated airplane. That's one without turbocharging, all right? In fact, don't try to fly there even with turbocharging, all right? So I just want to tell you that wind is the biggest factor. Okay? Another thing I want to mention to you is this. I'll ask you about this on the test. Class, this has a fancy name. This is called an altocumulus standing lenticular cloud. All right? Now, I had an optometrist in my class one day, and he knew what lenticular meant, of course. It means it's lens-shaped. If you see a cloud sitting over the mountain and it's lens-shaped, and it's standing there, that indicates that there's turbulence over the mountain. You see this sort of a cloud might form up here. They're going to ask you, what does it mean if you see an altocumulus standing lenticular cloud? And the answer is, it means a lot of turbulence over the mountains. Okay, I want to talk to you about fog. I want to talk to you about fog. And I want to tell you that there's two main types of fog I want you to know about. One of these is called radiation fog, and the other is called advection fog. Now, both types of fog, class, have the following. They both have a temperature inversion, all right? Both types of clouds have a temperature inversion, all right? They both have a temperature inversion. All right. Now, with a temperature inversion, we have warm air over cold ground. Let me tell you how radiation fog works. What we have, class, is we have the ground has become warm, and the ground has moisture in it. All right? The ground, and then we get a night when it's sort of clear and calm. The ground, this warm ground, acts like a radiator, and it radiates this warm air up over the ground at night. And with very little wind, we get a layer of warm air over the ground. By morning, the ground has become cold. So we have warm air over cold ground and a lot of moisture. We trap that moisture in the lower level, we have fog. All right? They say if you have a little teeny wind, 3 to 4 knots, it mixes this and makes the fog even deeper. In the morning, though, when the sun comes out and finally burns away this fog, then it clears up. But that's called radiation fog. Now, another type of fog is called advection fog. And here's a picture of advection fog. Now, what is advection? Well, what's convection? This is convection, isn't it? This is convection, the vertical movement of air. Advection is the horizontal movement of air. What we have is warm, moist air being brought up from over the Gulf of Mexico by a south-southeast wind, brought up over cold land. In this case, we have a wind of 15 knots. You know, a lot of times you'll hear people say, well, if the wind is picking up, that'll blow away the fog. Fact of the matter is, this kind of fog requires wind in order to exist. Okay? But radiation fog, a little bit of wind will blow the fog away. Here, wind is necessary in order for the fog to exist. So remember, just because you have wind, try to determine what kind of fog you have. Now I want to take a little time to talk to you about weather maps. I'd like you to open your yellow book now, your supplemental data yellow book. I'd like to open that, please open that to page 42. I'd like to tell you, class, that there are 4 weather maps that you should know about. You go to any FAA flight service station, you'll see these 4 displayed clearly for all private pilots to look at. One of these is the one you see in front of you on page 42. The other one you can see over there on page 43, which is the weather depiction chart, which shows sort of where IFR and VFR weather is. Then we've got the one on page 44, which is a summary of weather radar returns. And then we have the one on page 46, which is a forecast. That's something important to know. Of all 4 of those maps, there's only one that's a forecast, and that's called the Prague chart. The one we just looked at here, the last one, is called the weather Prague chart. Prague means prognostic, and that means prediction. It's important to understand that the previous 3 that we just mentioned are all history. Okay? Now what I'd like you to know is what is the main emphasis of the map on page 42, the surface weather map. Here's what I want you to know. I have instructional objectives, and my objective is that you know 2 things. 2 things. One is this map a forecast or is it history? And what is the main thing that this map shows me that the others don't show me as clearly? I want to tell you they're all history except the Prague chart. So here's the surface weather map. This must be history. And the main thing that this map shows me is the position of fronts, the centers of pressure, and the pressure patterns. Here's the front location. There's a cold front, a warm front, stationary front. Here's the centers of pressure. Here's a low pressure area. Here's a high pressure area. And it shows me the pressure patterns. Here you can see the isobars are all squiggly and undefined. So you could assume that the wind is kind of light and variable in this big center of high pressure. Here around this low, we see the isobars are more tightly packed. The wind is more defined, and the velocity is probably stronger. You can't read these little bits of detail around this weather station. You can't read that. They're not printed clear enough for anybody to read them. Those are for meteorologists only. The information you gain out of this is just as I say, the position of the fronts, the centers of pressure, so we can tell where the low pressure area is, the high pressure, and the pressure patterns. So we can see if the isobars are tightly compact, we're going to probably have strong winds. The next map I want you to look at is on the next page. This is called the weather depiction chart. The weather depiction chart. Now, the weather depiction chart is a map that shows us a quick reference. It shows us quickly where the IFR and the VFR weather is. But this is history. When I come to fly a trip in the morning, when I come to the airport to fly a trip that leaves at 7 a.m. and I get there at 6, it all shows IFR weather all over the place. But that's 3 hours, maybe 2 and 3 hours old. I have to check the current weather and see what the current weather is to see if there's been any changes. The current weather, which comes on the weather teletype reports, I'm going to check in a minute. So this one is sort of outdated. It's sometimes several hours old whenever you look at it. But look what it shows us. It shows us that here's a patch of IFR through the Midwest. Everything enclosed in this shaded area is weather below 1,000 and or below 3 miles. That's IFR weather. Now, we don't need to memorize that because it tells us this right down here, that the shaded area is where the weather is less than 1,000-foot ceiling and visibility is less than 3 miles. Now, the circled area that's not shaded, that's called marginal VFR. They call that MVFR. And that's where the weather is between 1,000 and 3,000 and visibility between 3 and 5 miles. And it tells us this. We don't need to memorize this. And the rest of this is good VFR. So what do we get out of this map? Take a look up here, class. We look at this and we say, the weather's IFR through the northern part of Illinois, southern part of Wisconsin, northern part of Indiana. We can see that the weather is IFR. It's marginally VFR out here in the east coast area, south of Pennsylvania, Virginia area. Okay, we can see that it's VFR up here in New England area. And reading these little stations along here, we don't need to do that because they're hard to read. They don't print very well on the weather printer. The main thing is just know what this map tries to show us. Now, let's go over here to the next map, which is the radar summary chart. The radar summary is also history. This tells us what the precipitation is that's being picked up by weather radar stations across the country. Now, radar tells us a little bit about the intensity of the precipitation. Now, we say that weather on these weather radar returns has 3 levels of intensity. Take a look up here. These intensity levels are intensity level 1, 3, and 5. This is an example of intensity level 1. This is an example of intensity level 3, and a circle within a circle within a circle is intensity level 5. Now, we don't call this light, medium, and heavy. They don't call it that. This is called moderate precipitation, this is called heavy precipitation, and this is called very heavy precipitation. All right? The idea being that light precipitation doesn't even show up on the radar summary. It doesn't show up on radar, so they can't put it on the radar summary. So this is considered to be moderate precipitation here. This is intensity level 3, which is heavy, and intensity level 5 is very heavy precipitation. So if we look at this slide right here, we can see that here we have moderate precipitation down around the St. Louis area. A little closer, a little further to the west, we have some heavy, and then we have a line of a very heavy. This would be called a squall line. This is a solid line of intensity level 5. A line here looks like it's about 80 miles long. This is a very long squall line. This is very intense weather. There's probably some tornadoes there. All this data we see around here we really don't need to know about, but basically this is telling us the average tops of these clouds. Average tops of these 18,000, 21,000, and so on. Here's some tops of 42,000. These are real big ones, right? So what you want to know as a pilot, when you go to look at this, you look at this and you can tell that this is history. This was a few hours ago. So you should get a more up-to-date information by trying to look at live radar. If you happen to be able to go out to the weather station at the flight service and you look at a radar summary, and if you think there's some problem with weather around your destination or whatever, ask them if you have live radar. Ask the flight service specialist if he has live radar you can look at. When you call for a weather briefing, I want you to get a captain complex, all right? What I mean by that is this. Don't let the weather briefer tell you everything. You'll never get to go flying if you do. Because they're trained to be very, very conservative. And if there's any forecast anywhere that says anything about bad weather, they'll read it to you, of course. They'll say, well, the radar summary, sir, shows intensity level 5 out in the area you want to go to. Well, that sounds real bad, all right. Then you say, well, do you have any live radar? Oh, yes, we've got live radar. Say, well, what does that show? Well, as a matter of fact, that shows all that weather's moved east to your area. Well, would I be able to, if I were just coming from the north, you think I'd be able, would that be further east? Well, it could be. Right now, it does show it has passed through there. So in other words, don't let him tell you everything. Ask a few questions. What you need to be able to ask some questions is some information, and the main information is timing, all right? This is history, and if he tells you that the weather, the information he's giving you is based on a radar summary, you know that that might be more than 2 hours old. Ask him, well, what do you show on the live radar if you have it? What's the current observation at Omaha or whatever? Okay? Now, let's look at the prog. This is the weather prediction chart. Now, the important thing to understand here again is timing. I'd like you to look at chart alpha and chart Charlie. And I'd like you to notice that chart alpha and chart Charlie both have the same valid time. Their valid time is 1200 Zulu, 1200 Greenwich time. Well, you might say, if they're both valid at 1200 Greenwich, why do they have them on two separate charts? Why don't they have them together? The reason is because it would be difficult to read. There's too much information packed on one weather map. So what they have is they have these split apart. Now, I'd also like you to notice that chart alpha is a low level. It says surface to 400 millibar. But notice that chart Charlie, that says that that is a surface prog. This is a prediction for only the surface. Well, what do I mean when I say that chart alpha is low level, surface to 400 millibar? All right, let me explain that to you. Take a look over here, class. At sea level, the pressure is approximately 1,000 millibars in metric numbers. When we get to 18,000 feet, the pressure is about 500 millibars. That's why we say that whenever we've gone to 18,000 feet, we've gone through half the atmosphere. Now, meteorologists, they talk in their own language. If you were to call the weather service and ask them what's the wind at 18,000 feet, the wind's aloft at 18,000, you probably hear them say, hey Jack, what's the wind at the 500 millibar level? They talk in terms of millibars instead of altitudes. That's just sort of scientific to talk that way. They like to talk scientific. Now I'm going to tell you a fact, and that is that 300 millibars is 30,000 feet. I remember that because 300 and 30,000 kind of sound about alike. And I can remember half the atmosphere at 18,000 feet. Now this chart says that it's from the surface to 400 millibars. Just take a guess. What altitude do you think is equal to 400 millibars? It's a nice round number. 24,000 feet. All right? So, I want you to know that chart alpha, this is a forecast from the surface to 24,000 feet. That's what that says there. Now, chart alpha forecasts certain things. Here's what it shows us. Take a look up here. It forecasts sort of like the weather depiction chart. Look at here, class. It forecasts where the weather will be IFR. Everything circled is where the weather will be IFR. Everything shown in scalloped will be MVFR, or marginal VFR. What else does it forecast? Not only does it forecast the surface, but it forecasts turbulence. Anything shown in dashes represents moderate or greater turbulence. In the northern part of these dashes, you can see that this shows turbulence up to 24,000 feet. In the lower part of this circled dashed area down by Texas, Louisiana area, it shows turbulence up to 20,000 feet, moderate turbulence. If you get out over California here, this shows some turbulence, moderate turbulence, up to 18,000 feet. All right? What else does this show? Take a look here in the legend. It shows the dots show the freezing level at the surface, and the dashes show the freezing level above the surface. Take a look up here. I'd like you to notice that right about through Chicago, if you follow this dashed line off all the way to the Atlantic Ocean, you'll see a number 80 tagged on that. That means that the freezing level over Chicago is 8,000 feet. That's what that means. All right? Now, if you want to know the freezing level in Milwaukee, you'd have to kind of interpolate. and say, well, let's see, further to the north towards Green Bay, for example, the freezing level is 4,000. It's a little lower. So the freezing level over in Milwaukee, you might say that that's, maybe 7,000 feet or thereabouts. Okay? So this is the forecast for 1200 Zulu from the surface to 400 millibars. Now, chart Charlie, this shows the forecast for the same time, but only on the surface. And this predicts where the position of the fronts will be and what kind of fronts we'll have. Also, if the area is shaded, it indicates more than a 50% probability of precipitation falling on any one spot. If it's not shaded but simply enclosed, that means less than a 50% probability. Now there's a legend that tells you things like this. You can probably guess at them. Out here in the west, you see there's an area here that's forecasting more than a 50% probability of some kind of precipitation. And these things look like snowflakes. So you might guess then that they're forecasting more than a 50% probability of snow. Whereas out here in the upper Midwest, they're forecasting some rain in the southern portions, and they're forecasting rain mixed with snow in the northern portions here. You can kind of tell just to look at it. You can guess what it is. Now some of you might be saying this. Take a look up here. Some of you might be saying, wait, I don't understand what you mean when you say this is 1200 Zulu, and then beneath it it says it's a 12-hour prog. What does that mean? Well, let me explain it to you. When this is a 12-hour prog, let me tell you what that tells you. That gives you an idea as to the credibility of this forecast. That's what it tells you, the credibility. Tell me this. If you went and saw a forecast that was valid for today, but was created by someone a year ago, how valid is that forecast going to be? Not too good. That's a 365-day forecast that's valid today, but created a year ago. It's not worth a darn. If you saw one created 2 weeks ago, it's probably not very good. But if you saw a forecast that's valid at 1200 Zulu, and it was created only 12 hours before that valid time, there's a good chance this forecast is going to be relatively accurate. Now, chart Bravo and chart Delta, they're valid at midnight Zulu. In other words, 12 hours later is the valid time. Naturally, since they're on the same piece of paper and created by the meteorologist the same time he created chart Alpha and chart Charlie, naturally this is a 24-hour forecast. All right? So the period of time shown here, that indicates the credibility of the forecast. That's what it really shows us. Now, is this true? Tell me this. Would it be correct to say that the chart here and chart Alpha, that shows the weather for 12 hours before 1200 Zulu? For a 12-hour period before 1200 Zulu, would that be a correct statement? No. No, that's not correct. Only correct statement is this. Here's the correct statement. Chart Alpha shows us what the weather should be at exactly and precisely 1200 Zulu. That's what this forecast tells us. All right? And when chart Bravo says that the valid time is midnight Zulu, it's telling you that's what the weather should be at midnight Zulu. That's all it's telling you. It's not a minute before or a minute after. That's what it's forecasting. Now, if you want to know what the weather is going to be like at 1800 Greenwich, then you've got to interpolate between Alpha and Bravo, for example. If you want to know what the weather is going to be like at let's say, for instance, 1000 Greenwich, 2 hours before this valid time, you'd interpolate between current weather and forecast. See? Notice how you can kind of interpolate. Look how the weather is going to be here at 1200 Zulu, and look what it's going to be a little later. It's going to move further to the east there. You see? Okay, I'd like you to turn to page 40 now, please. Turn to page 40. And we've got some teletype reports. I'd like to tell you that these reports you see on page 40, the report there on page 40, which is figure 7, 8, and 9, these come off of a teletype machine that might look like this. This is a very, very old printer. This is like World War II type printer, all right? There are much more modern high-speed printers now, but anyway, they all print the same kind of thing. And this is what they print. They print weather reports like you see here in figure 7. Now let me tell you, class, the main type of reports that I want you to be familiar with are the actual station observations shown in figure 7. All right? These are observations for each station which are transmitted every hour on the hour. Figure 8 shows forecasts for each station. These are 24-hour forecasts. These are called terminal forecasts. Figure 9, these are winds aloft forecasts. These are forecasts of the winds aloft for flight planning purposes. These also come over that teletype report. There are also some other kinds of things, such as you see in figure 10 and 11 on the next page, which are area forecasts, which are sort of pages of like a paragraph or two describing what the weather is going to do, sort of trying to give you a picture map in your mind, and figure 11, which is in-flight advisories, which are called airmits and sigmits and so on. Okay, let's go back to page 40 though, and let's talk specifically about this weather report here. The first thing I'd like to talk to you about this though, I'd like to talk to you about the time of this report. You notice on the bottom of page 39, there's a little conversion chart that shows us how to convert from local time to Greenwich time. Well, what do we mean by Greenwich time anyway? Well, I'll go back here to page 40 here, and I want to point this out to you. I'd like to point out to you that this report was taken on the 18th day of the month, and it was transmitted as the 1300 Greenwich report. Now, the actual time of the observation was 12:51 Greenwich, but it was sent in and was transmitted with the 1300 report. Right? That's 1300 Greenwich. Now, Greenwich means that it's on the world clock. All right? This is called Greenwich time. They have a new name for this now. I think it's called Universal Coordinated Universal Time, but I'm going to call it Greenwich for the rest of my life. That's good enough, okay? Anyway, this report is at 1300 Greenwich. All the weather reports are in Greenwich, and here's the reason why. All of the early navigators and things, as they navigated the world by ship, they kept track of time in their home base log. They kept track of time in Greenwich time, which was Greenwich, England, the home base for the English ships of the world. So they kept all their logs in home base time. So whenever they came upon Hawaii, they didn't say we just came on Hawaii and pulled into some bay there at noon Honolulu Standard Time, because they didn't know Honolulu was, of course. So they would keep track of it in Greenwich time. So all the weather reports and everything is always in the world clock. What a nightmare it would be if you got the latest weather for Boise, Idaho, and you weren't sure whether Boise, Idaho was in mountain time or West Coast time. What a nightmare it would be if those reports were in local time. So they're always in Greenwich time. What we have to do is we have to convert our own time to Greenwich, and then we can tell what time the report is for. Let me give you an example. Take a look up here. Now, as I look at my watch, I see that the time right now is 3:20, all right? 3:20 p.m. Of course, 3:20 p.m. in military time is 15:20. Now, right now, the time here is 15:20, and let's say we're using Central Standard Time. 15:20 Central Standard Time. Well, if we go to this chart that you see on page 39, it shows if you want to convert to Greenwich time, we look down here and we see that for Central Standard Time, to get Greenwich time, add 6 hours. That means that the sun has already passed Greenwich, England 6 hours ago. So we add 6 hours to this, and that means that the present time in Greenwich, England, adding 6 hours, is 21:20. We put a little Z there denoting Zulu, which means Greenwich time. So the time all over the world right now is 21:20. If you called someone up in California class and you asked them, you got on the phone and you said, what time is it there, Greenwich time? What would he say the time is? 21:20. So if you looked at the latest weather report for California, all you'd look for would be the latest weather, which would be the 2100 observation. If you had a friend and he lived in Nairobi, Kenya, and you called him and you said, say, what time do you have there? Greenwich time? He'd say, well, of course, it's 21:20. The whole time in the whole world right now is 21:20. So this allows us to know, once we convert ourselves onto Greenwich, I have a watch that always reads Greenwich time, in addition to local time, but it reads Greenwich, so I always know what time it is Greenwich, no matter what time zone I'm in, because I know what time it is on the world clock. And if I want to look at the latest weather, I'd look for the 2100 weather for wherever I'm going to. I say, oh, let me check the latest weather. And if I see a weather report, I know if it's the latest, if it's the 2100 observation. Okay, now this observation here is the 1300 observation. However, you might be asked to convert back to a particular time zone. All right, well, they're going to give you this that you see on the bottom of page 39. Now tell me this, what's the conversion to Mountain Standard Time? How many hours difference is that? 7. Of course, that's 7 if you want to convert to Greenwich time. Well, this is given in Greenwich time, and if I want you to convert to Mountain Standard, you'd subtract 7, and that would mean that the correct time is 06 Mountain Standard Time. Right? Now you're going to have a problem on the test, one problem, where you have to convert local time to Greenwich or Greenwich time back to local, or some particular local time. Might be Mountain Standard, might be Pacific Daylight, whatever. But you'll be given the chart like you have on bottom of page 39. You'll be given this chart right here. It'll be no problem. Okay? Alrighty. Really quite simple. You have no problem with that, I'm sure. All right, now let's talk about reading these weather reports a little bit. Take a look up here. We'll talk about reading these weather reports. I'll just cover reading some real simple ones real quick, and then we'll talk about reading some harder ones. For instance, here we are with Rapid City, and the first thing we have here is we have the sky coverage. This shows 25,000 thin scattered. Now, just to tell you a few things here, the way they make their zeros is with a diagonal line through them. I don't know why, it's so you don't confuse it with a circle. But anyway, they don't use any circles. So anyway, 25,000, and the dash is read as thin. You might want to circle that, note that that means thin. 25,000 thin scattered. Visibility, 15 miles. So it's always sky coverage and then visibility. Why don't you mark this in your book there on page 40 there, that the first thing is the sky coverage. So the first thing is 25,000 thin scattered, visibility 15 miles. It's always the same order. They call these sequence reports because they're always in the same sequence. 25,000 thin scattered, visibility 15 miles. Now the pressure in millibars, we skip that. That doesn't apply. That's for meteorologists only. Temperature's 36. The dew point is 21. Now the wind here is 190 degrees at 9 knots. But take a look here, class. Let me show you something. They always show the wind in a 4-digit number only. So if we have wind of 190 at, what was that, 9 knots there? 190 at 9. If the wind was 190 at 19, they would say 1919. This is a wind of 190 degrees at 19 knots. Now, if the wind the fact is that this is a direction of wind to the nearest 10 degrees. This might actually be a wind of 185 degrees. And they've rounded it off to 190. So it's always the wind in the nearest 10 degrees is the first two numbers, and the last two numbers is the velocity of the wind. Now the next thing we have here is the altimeter setting. The altimeter setting it shows here as being 29.59. You might wonder, where's the 2? Well, the FAA, or the National Weather Service, has been on a big kick to save ink for the last 44 years. All right? So far, over the last 44 years, they've saved a total of 21 bottles of ink by leaving off that 1 digit. Okay, here's what I mean. The altimeter setting, class, take a look up here, is probably never less. I've never heard of an altimeter setting less than 28 inches of mercury, and I've never heard of it much higher than 32 point something. So you see, they figure there's no need in printing this first digit, because all pilots have to be smart, you know. So they figure that you could figure it out if they just gave you the last 3 numbers, and then they could save that ink. They want to save ink. So the altimeter setting, the missing number here must be 2. This couldn't be 3. It couldn't be 39.59 inches of mercury. The altimeter setting, which is the same as a barometric pressure, must be 29.59. Okay, let's look at the next report. The next report for Scotts Bluff says they have 20,000 thin scattered, visibility 25 miles, pressure in millibars we skip, temperature's 27, dew point 19, wind is 080 degrees at 5 knots, altimeter 29.74. No problem. Okay, let's go down here to another one here, and maybe I'll ask a volunteer. Let's see, Colin, could I ask you to volunteer? Would you mind trying to read one of these? Okay, let's take a look at the third one there for Sydney. See if you can get Sydney.
No ceiling, or clear.
Exactly, it's clear. It says clear.
20,000.
And visibility comes next.
20 miles.
20 miles visibility. What's this here?
Millibars.
That's the millibars we skip for meteorologists only. Very good.
32 degrees.
32 degrees temperature.
27.
27 dew point. Very good.
280 at 12 knots.
Wind is 280 degrees at 12 knots. Very good.
29.75.
29.75. Right on. Super. That's great. Thank you very much. Let's take a look at this next one. I'd like to point out something to you. I'd like to point out to you that the definition of a ceiling, class, and you want to know this for all of your aviation career, this is always asked on all written tests. A ceiling is defined as the lowest layer of broken, overcast, or obscured clouds, which is not shown as thin. Okay? Here's some clouds here at Casper, which have 14,000 scattered, 25,000 thin, broken. Visibility 15 miles. Do we have a ceiling here at Casper? The answer is no. We have a broken layer, which would normally be considered a ceiling, but it's not a ceiling because it's a thin broken. All right? Only a real broken would be considered. If it said 25,000 broken, that would be considered a ceiling. But a ceiling is defined as the lowest layer of broken, overcast, or obscuration, which is not shown as thin or partial. In the case of an obscuration, they call it thin. They don't call it thin, they call it partial. Okay, so we have 14,000 scattered, 25,000 thin, broken, visibility 15 miles here. Now let's go down to Casper for a minute. Correction, go to Cheyenne. Look at Cheyenne. Cheyenne has 25,000 broken, visibility 15 miles. Do they have a ceiling at Cheyenne? That's the question I have right now.
Yes.
The answer is they certainly do. And that ceiling is 25,000 broken. It's not shown as thin, so it's 25,000 broken. Now they do a funny thing. Anytime we have a ceiling, they always tell you how the ceiling was obtained by the use of a letter. It may be the letter E for estimated. It may be the letter M for measured. It may be even a letter W for meaning it's an indefinite ceiling. They're not sure what it really is, but they'll always tell you how the ceiling was obtained. They'll have a letter there. So the letter will always help you on the test if they ask you how high is the ceiling. If you're not sure whether thin, broken counts, if it doesn't have a letter, such as 25,000 thin, broken, that's not a ceiling. But here we have a letter, so that tells us where the ceiling is. It's 25,000 broken. It's an estimated 25,000 broken. All right, now let me show you something else that doesn't really pertain to meteorology here. We'll have to continue reading this. But notice they have 25,000 broken, visibility 15 miles. Pressure millibars we skip, temperature 42, dew point 21, wind is 270 degrees at 8 knots, and the altimeter 2980. Now take a look here, class. Look at these funny numbers. At the end of this, it has these funny little arrows. It says 10/5 and 11/1. Let me tell you what this means. This means that there are two NOTAMs in effect for this airport. You remember a little earlier I told you that the most up-to-date type of NOTAMs are the NOTAMs that are carried in the FAA's telecommunication system? Well, this is exactly what I mean. If you're about to take off from an airport, and if there's a NOTAM that's important to know about, all right, any NOTAM that's important to know about will be carried at the end of the report here. And this says that the 5th NOTAM of the 10th month and the 1st NOTAM of the 11th month are current and in effect. And you should find out what they mean. You can call the FAA and ask them what those are. Now sometimes they write it right with the weather report. Most often they don't, though, in which case you want to call flight service and ask them what they are. But the NOTAM, the 5th one of the 10th month for Cheyenne says that the Cheyenne runway lights on runway 12 and 30 are out of service. It also says that runway 12 and 30 is closed between 1500 and 2300 hours weekdays. So these are the most current, most up-to-date kind of NOTAMs. These are different than those ones you get in the mail, which you subscribe to. For instance, if you were going to O'Hare and a large plane has just become disabled on the runway, and one of the longest runways at the world's largest, busiest airport has just been closed, you think that would be important to you planning a flight to O'Hare. Darn right, you want to bring along a lot of extra fuel for holding. Or you may want to plan to go to another airport because you don't want to hold for 2 hours. Let's look on page 39 in our yellow book, our supplemental data book, and this is the key to aviation weather reports. Except on your FAA test, they don't give you this. But it's so simple, you only got these 4 questions. Right? This is the key to aviation weather reports. Now this is a report for Kansas City. It says Kansas City, looking at this sample forecast, will be 1,500 scattered and a measured 2,500 overcast. Down below here, look at here, class. The legend tells us that here that E is estimated, M is measured, W is indefinite. V means variable. Anyway, they're going to have 1,500 scattered, measured 2,500 overcast. They're only going to have 1 mile visibility. Now, anytime the visibility is being restricted less than a certain amount, something like 8 miles or whatever, they'll tell you what's restricting the visibility. And you see this list of letters? This is a list of FAA-approved things that can possibly restrict visibility, all right? Now, R stands for rain, and K stands for smoke. Now, they don't use S for smoke because they use up S for snow, all right? All right, anyway, we have 1 mile visibility in rain and smoke. But, take a look up here, class. Look at this. Look what this says here. It says precipitation intensities are indicated thus. 1 dash means light. No sign means moderate. And a plus means heavy. All right? So, now your plus probably didn't print, so you might write that in there in your book there. That the plus means, the plus applies there. Plus is heavy. All right? Right there where it says precipitation intensities are indicated thus. 1 dash is light, no sign moderate, and a plus means heavy. Okay? All righty? So, what we've got is 1 mile visibility, but here's a tricky way that you have to read this. We have 1 mile visibility, and it's light rain and smoke. You might say, well, your airworthiness, how do you know it isn't rain and light smoke? Well, because this code only applies to precipitation. So it must be 1 mile visibility in light rain and smoke. All right? Now, pressure in millibars we skip, and of course there's your temperature and dew point, 58, 56. Wind is 180 degrees at 7, altimeter 2993. The rest of this is remarks for meteorologists only. All right, at least for now it's for meteorologists. Now, let's go back to our forecast there that we were reading on page 40. It's actually on page, we were looking at this on page 40. Let's look at the weather for JFK and for Midway. For JFK, here's the way we read this. Take a look up here, class. This is the symbol for obscuration. It tells us this on the legend. You might think this is thin obscuration. However, we technically read that as partially obscured. It's not a ceiling, though, because it's sort of like thin. All right? And thin doesn't count, nor does partial. This is a partially obscured sky with a measured 700 feet overcast, visibility 1.5 mile in heavy rain and fog. Temperature 63, dew point 61, winds 320 at 5, altimeter 2980. The rest of these remarks don't worry about. Now, JFK, this is a very hard one here. Would someone like to try, could I ask you to try reading this one? This is the hardest one by far. See if you can read the JFK one here.
The W says indefinite.
Very good. The W means indefinite. It just means there is a ceiling, of course. That qualifies as a ceiling. So it's an indefinite.
500.
Obscured.
1/2 with fog.
1/2 mile visibility with fog. Very good. Excellent.
Temperature 68, dew point 64.
Okay, temperature 68, dew point 64.
Winds are 180 at 04.
Okay, the winds are 180 at 04.
And the barometer is 30.06.
Altimeter 30.06. So we started out here with an indefinite, 500 feet, sky obscured. Visibility a half in fog. Skip the millibars, temperature 68, dew point 64, wind 180 degrees at 4, altimeter 30.06. Now let's take a minute and talk about the terminal forecasts, all right? The terminal forecasts on figure 8. Figure 8 shows terminal forecasts. Take a look up here, class. Let me explain these to you. This is on page 40, of course. The terminal forecasts are 24-hour forecasts for each station, all right? For instance, if we go here to Gage, there's Gage, Oklahoma. Here's an important point. Notice the 011515. This is an area that's very confusing to people, but you must understand here, it means this. This is a forecast that becomes valid on the first day of the month at 1500 Greenwich. And it's valid through and until, we should say, until 1500 Zulu the next day. That's what the 1515 means. See, that's confusing to people. I want to be sure you understand this. The 1515 means that it's a 24-hour forecast. It's from 1500 Zulu on the first until 1500 Zulu on the second. Now, beginning at 1500 Zulu, Gage says that they're going to have 10,000 scattered, 25,000 scattered, and the wind is going to be 260 degrees at 10 knots. Now, let me tell you something. They leave things off here. Let's look at this on page 39 for just a second. The Keyed Aviation Weather Forecast talks about terminal forecasts. It contains information for specific airports on expected ceiling, cloud heights, cloud amounts, visibility, and weather and obstruction to vision. Now, it says they're issued 3 times a day and are valid for 24 hours. So a 24-hour forecast. It says the last 6 hours of the forecast are covered by a categorical statement indicating whether VFR, marginal VFR, IFR, or low IFR conditions are expected. Ceiling is shown by a C. They don't have the M for measured, all right, and the E for estimated. They just use a C for ceilings. But underline this under visibility. Visibility is in statute miles, but omitted if over 6 miles. So they don't show the visibility if it's over 6. Surface winds in tens of degrees and knots and omitted when less than 10. They don't show the wind unless it's going to be 10 or more. All right? So, going back to reading this that we had here, take a look here at gauge again. Gauge is forecasting at 1500 Greenwich to be 10,000 scattered, and another layer at 25,000 scattered, and a wind of 260 degrees at 10 knots. So class, tell me this now. How much visibility will we have at this time?
Over 6 miles.
Over 6 miles. That's all we know. They don't forecast the temperature or the dew point or the altimeter setting. By the way, circle this 260 at 10. Note off to the side that that's the wind. It's been my experience from training thousands of students that people get confused when they see that 4-digit number. They don't know what that is. They want to call it temperature and dew point. Some want to call it the altimeter setting or something. But anyway, that 4-digit number is the wind and velocity. All right, now, here's the important thing, class. Listen carefully. This is showing the wind that it will be the wind and the weather, all the weather, for only a 1-hour period. This is for only a 1-hour period. This is until 1600 Zulu. When they have this period, that means that's the end of that forecast. Now we got a new forecast. Beginning at 1600 Zulu, the weather is going to be 6,000 scattered and a ceiling of 10,000 broken. Visibility will be good because they don't show it, but the wind will be 330 degrees at 15 knots, gusting to 22 knots. With a chance of ceilings 5,000 broken, 5 miles visibility, thunderstorm and rain shower. Now tell me this, class. How long will it be like that? How long will it be like that, class?
201.
Until 0100 Zulu, which would be 9 hours. From 16 till 2400, that's 8 hours. And it's going to be like that until 01. That's a 9-hour period. Now the next period from 01 until 09 shows that we're going to have, that's an 8-hour period. Here's what you're going to have during that 8-hour period. 25,000 scattered, winds 350 at 15, gusting to 25. And after 0900 Zulu, which is always just the last 6 hours, they always give just a categorical outlook. That's all they ever have. It'll categorically be VFR. And when it says wind, I believe that means the winds are going to be more than 25 knots, possibly, occasionally. All right? So that's how we use this. Now, for instance, if you were flying a trip, take a look up here. And let's say, for instance, you were flying a flight and you were going out to, maybe you were going out to Miles City or someplace like that. If you're going out to Miles City and you think you're going to take off and you figure it's going to be 6 hours flying time and you figure you're going to get there at 2200 Greenwich, all you need to do is underline the weather for what it's going to be when you arrive. If you're going to arrive at 2200 Greenwich, this is what you'd have. A ceiling of 3,000 broken, winds 180 degrees at 15 knots, gusting to 22 with a chance of ceilings 2,000 broken, 1 mile visibility, thunderstorm and rain shower. Okay? Figure 7, 8, and 9. I want to mention that figure 7 and 8, all of these cloud observations are above ground. That's very important to understand. I'll say that again. Figures 7 and 8, all of these cloud observations are above ground. We're now going to talk about figure 9, which is a winds aloft forecast. And I'd like you to know that the winds aloft forecasts are given above sea level. Let's zero in on figure 9 here, and let's talk about the winds aloft forecast. Take a look up here for a moment, please, class. I'd like to point out to you here that at Abilene, the winds at 9,000 feet will be 250 degrees at 19 knots, and the temperature will be +9 centigrade. All right? Now, I'd like you to know that if you continue going to higher altitude, you'll notice that when you get to 30,000 feet, it doesn't show that the temperature will be minus, for instance, -40 or whatever. Here at Abilene at 30,000 feet, the wind will be 230 degrees at 48 knots, and it doesn't say minus because they're trying to save ink again. They're on a save ink kick, but the temperature will be -40. And they ask you this on the test. Circle this right here. It says temperatures are negative above 24,000 feet. Temperatures are negative above 24,000 feet. All right, now class, I want to point out something they'll ask about on the test. At Abilene, they don't show any wind at 3,000. At Albuquerque, they show no wind at 3,000 or at 6,000. Why is that?
It's higher.
Sure, the ground elevation at Abilene, 6,000 feet. Of course there's no wind at 3,000. That's below the surface of the ground. These winds are above sea level. Now another thing is this. This is important, and I'll ask you this on a test. They don't show the temperature at the lower altitude winds aloft. Because the lower altitude winds aloft, it's too much influenced by the surface temperature. So they just don't show the surface temperature in that case.
altitude, to spin, or all three. As you add power in slow flight, the nose of the airplane will turn to the left because of torque. Right rudder must be applied to counteract torque and to maintain a constant heading. It is important to remember that by increasing the power and by using the elevators together, you'll be able to maintain altitude and airspeed. If the airspeed decreases too much, add power and control the altitude with the elevators. Note that a climb in slow flight may not be possible due to insufficient power in excess of that required to maintain straight and level flight. This inability of the airplane to climb at a slow airspeed, even with maximum power, is often referred to as operating on the backside of the power curve. In recovering from slow flight, you should add power and reduce the angle of attack carefully in order to maintain altitude. As the airplane reaches cruising speed, adjust the power and retrim the aircraft. You should understand that a stall is caused by the breaking up of the smooth flow of air over a wing or other surface by an excessively high angle of attack. Your instructor will demonstrate the stall, and you'll note that it is apparent by a sudden loss of flight control effectiveness and, in some cases, an uncontrollable pitching of the nose. The most common cause of a stall is the failure of the pilot to maintain airspeed adequate for his flight situation. For this reason, your instructor will introduce simple stalls in conjunction with the instruction of flight at minimum controllable speed. Your instructor will introduce stalls into your basic curriculum for two reasons. First, to assist you in recognizing a stall before it's too late to take corrective action, and second, to develop the habit of taking prompt and effective preventive action. Prior to flight instruction in stalls, your instructor will point out several indicators to watch for in the stall. These indicators are visual, auditory, and kinesthetic impressions, the feel of controlled pressures, and flight instrument indications. Beginning flight instruction in stalls will be given at an altitude considerably higher than the one normally required for stall recoveries. All stalls require the expenditure of power, altitude, or both for a recovery, and in order to prevent any unnecessary apprehension on your part, your instructor will usually perform stalls at no lower than 2,000 feet above ground level. The longer it takes you to sense the approaching stall, the more complete the stall is likely to become, and the greater the loss of altitude that can be expected. Your instructor will insist that clearing turns be performed before entry into power off or power on stalls. Normally, the clearing turns should be used prior to all maneuvers. Clearing turns may be executed in two different ways, by performing a 90-degree turn in one direction followed by a 90-degree turn in the other, or by performing a 360-degree turn in either direction. In making clearing turns, it is important to look behind you in the direction of the turn before the airplane banks. During the turn, look for other aircraft above and below you. Now you're ready for the straight-ahead power-off stall. Your first step is to apply carburetor heat and then retard the power smoothly to idle. Now you will apply back pressure smoothly, gradually increasing it in order to hold the nose above the horizon. As you do this, your instructor will ask you to note the changing airspeed indications, the attitude indicator, and the outside horizon. Slightly above the stall speed, the warning indicator will be activated. In order to maintain directional control, it is important to keep your ankles flexible and relaxed so that you can use the rudder freely. Apply rudders as necessary to keep the airplane moving in the proper direction. It's also important to coordinate the rudder with the aileron controls. After the nose is firmly raised with the elevators to an attitude which obviously will prevent further gliding, you can expect the stall at any moment. Your instructor will point out that a certain attitude based on experience and knowledge of the characteristics of the airplane must be determined. The attitude should be steep enough to prevent mushing or settling, but should not be so steep as to cause alarm and tenseness on your part. You will be shown that this attitude can be estimated from the angle the wingtip makes with the horizon, from the indications of the attitude indicator, and from the height of the nose above the outside horizon. To recover from a stall, relieve the back pressure on the control wheel and immediately reduce the angle of attack. This should be done smoothly and quickly until the nose is slightly below the horizon, at which point the wings will recover their lift. In the stall recovery, it's important to maintain directional and lateral control by the coordinated use of the controls. Remember that the rudder is more effective than the aileron. You should avoid abrupt use of the ailerons during a stall recovery. As soon as you relieve the back pressure on the elevator and start the recovery, it's important to add full power. After you have completely recovered, assume straight and level flight. Adjust the power to cruise and retrim the aircraft in order to maintain altitude. Your instructor will explain the correct procedure for the recovery from all stalls and he'll emphasize the importance of immediately reducing the angle of attack as you simultaneously apply power. This will be explained and demonstrated as it applies to all normally foreseen flight situations. To review stalls, several important points need to be stressed. First, at the indication of a stall, the nose is lowered positively and immediately. The amount of control force or movement used depends on the design of the airplane and the severity of the stall. In some airplanes, moderate action of the control column, perhaps slightly forward of neutral, is enough, while in others a forcible forward pressure is required. You should understand that a reversed load can be thrown on the wings, which may impede rather than speed the stall recovery. The object of your recovery is to align the wing chord with the direction of the relative wind. In stall recovery, all available power is applied. The throttle should be opened smoothly but promptly. And if the throttle is jammed open, some engines may cough and sputter, while others with high-speed turbochargers may be severely damaged. Because of the low airspeed, full power applied at the instant of a stall will not cause overspeeding of the engine equipped with a fixed-pitch propeller. It will be necessary, however, to reduce the throttle setting as speed is gained in the recovery. The tachometer needle should never be allowed to pass the red line. Straight and level flight will be regained with the coordinated use of all controls. During your instructor's demonstration and your practice of stalls, the heading should be maintained with liberal use of the rudder. Full recovery from a stall should be planned to produce a safe recovery with the least expenditure of altitude. Altitude loss in recoveries from full stalls should not exceed 200 feet normally. Diving steeply will hasten the recovery from the stall, but will cause a greater loss of altitude, which might be critical in an emergency recovery from an inadvertent stall near the ground. Power off stalls should be practiced from both straight glides and 10 to 30 degrees banked gliding turns. In stalls from gliding turns, care must be taken to see that the turn continues at a constant angle of bank until the stall occurs. The recovery is made straight ahead with the least loss of altitude and is effected in accordance with the standard recovery. If the gliding turn is not properly coordinated with the approach of the stall, wallowing or rolling may result when the stall occurs. If the airplane is in a slip, the top wing may stall first and whip down abruptly. If the top wing does stall first and whips down abruptly, the recovery procedure is not affected in any way. The stall is broken, heading maintained, and the wings are leveled by coordinated use of the controls. All the principles which apply to stalls without power also apply to stalls entered with power, although there are some important differences in the maneuvers. These differences will be pointed out as we continue. First of all, the pitching of the airplane resulting from a power stall condition with at least 65% power is much more steep and rapid, and the airplane is harder to handle than during power off stalls. During a power on stall, there is a tendency for the airplane to fall off on one wing or the other more readily than in a power off stall. The elevators retain their positive control longer and require the nose to be raised higher to accomplish the power stall. The rudder remains much more effective due to the presence of the slipstream. The ailerons seem to be less effective and establish an entirely new relationship in relative control effectiveness. This is partially because power application causes the stalling speed to be lowered slightly, which decreases the effect of the ailerons. In airplanes of relatively high horsepower, a torque effect will be encountered which makes the yaw control more difficult. This tends to aggravate the pilot's normal tendency toward over-controlling and causes walking of the rudder, which should be discouraged because any violent movements will act as a brake and further decrease the airspeed. The difference in the relationship of the relative control effectiveness is due to the fact that the power being applied lowers slightly the stalling speed, which increases aileron effectiveness. At the same time, the slipstream keeps the elevator and rudder effective at a slower speed. Here are three types of power-on stalls: the partial stall, the normal stall, and the complete stall. To perform the partial stall, you will set your throttle at cruising RPM and apply back elevator pressure. Notice that the airspeed will decrease. Just prior to the stall, you will reduce the angle of attack with the elevators and apply full throttle to recover. You will enter the normal power-on stall the same way that you enter the partial stall, except that you will hold the back elevator pressure until a definite stall occurs. Then you'll begin your recovery. The complete power-on stall is entered with cruising power. You will gradually apply full back elevator pressure until the complete stall occurs and the nose falls through the horizon. To recover from the partial, normal, and complete power on stalls, back elevator pressure is released immediately. Full power during a recovery is applied to avoid any unnecessary loss of altitude. In power on stall recoveries, your loss of